Hello APC Mechanics in Unit 7 Gravitation, Class 5, 7.2, Orbits of Planets and Satellites, Part 1. Then Section 1, Conservation of Angular Momentum, Planetary Motion. Previously we have determined the orbital speed v and the orbital period t of planetary motion, and they are given by the following. These relationships work perfectly if the orbits are circular, as we have mentioned. In reality, planetary motion is dictated by elliptical paths. An ellipse is a stretched circle with two foci. And for planetary motion, the massive body, say for example planet Earth, is or coincides with one of the foci, and the less massive body, say for example the Moon, orbits Earth along an elliptical path. Then these are the two foci of the ellipse. The more or the central mass will be situated at one of them, in which the other mass will be rotating through an ellipse. As the Moon orbits Earth, R varies, and hence all V and T change as well. Here we're assuming that the Moon only admits tangential velocity at all times. Now, however, V and R for different locations can be still related to each other using conservation of angular momentum. What I'm trying to say here, if you notice carefully, from the geometry of the ellipse, as the Moon orbits the Earth, R changes, which makes V and the period change. And these two relations, they break down. However, so V and T cannot be calculated in this case, but yet we can always use the conservation of angular momentum in order to find the relation between V and R and basically T. The forces acting on the Moon are the pull of gravity, but the pull of gravity produces no torque. That is, the torque net is equal to 0, and dl by dt is equal to 0. Now, why the pull of gravity produces no torque on the Moon? Now, this is the axis of rotation, and notice that the pull of gravity, the line of action, passes through the axis of rotation. Then it produces no torque on the Moon. Now, what are the forces that are acting on the Moon? We have only the pull of gravity. If the only force that is acting on the Moon is the pull of gravity, and the pull of gravity produces no torque, which means the net torque on the system is equal to 0. Now remember, for translational motion, F net is given by the variation of momentum. And if it happens, if the net force is equal to 0, this means dp by dt equals to 0. And if the derivative of a function is 0, it means that this function is constant. And by constant, it means it is conserved. Now here, similarly, because the only force is acting is the pull of gravity, and it produces no torque, which means torque net is equal to 0. And for rotational motion, torque net is related to the derivative of the angular momentum. Then dl by dt is equal to 0, which means the angular momentum of our system, which is the orbit, the mass in motion, which is the Moon, is conserved. Which means the angular momentum of the Moon is conserved, it is constant, which means initial angular momentum is equal to final angular momentum, which means I1 omega 1 is equal to I2 omega 2. Now, remember, the definition of the angular momentum is given by I multiplied by omega, in which I is the rotational inertia and omega is the angular speed or velocity. The rotational inertia of the Moon around the planet is given by mr square. Now, the Moon is considered to be a particle in comparison with the Earth. And we know that the rotational inertia of a particle about a certain axis is given by mr square, where m is the mass of the Moon and r is the center-to-center separation distance, and we know that omega is equal to v over r, where v is the speed of the Moon orbiting the Earth. Then we have that mr1 square multiplied by v1 over r1 is equal to mr2 square multiplied by v2 of r2. So I have replaced I by mr square and omega v over r. Now here we can apply the cancellation effect for the masses on both sides, and this with the power of 2, similarly here, and we're left with r1 v1, which means, now what does the point 1 and the point 2 represent? The point 1 is a point on the ellipse, and a point 2 is a different point. Now v1 would be the speed of the Moon at this point, and v2 would be the speed of the Moon at the point 2. Recall that because r changes, then the speed of the Moon at each point change. R1 would be the separation distance from this point to this point, as well as for R2 from this point to that point, which means that R1 multiplied by V1 is equal to R2 multiplied by V2. This relation can be used in elliptical planetary motion to correlate V and R for different positions. Remark, as seen, the quantity RV is equal to constant due to the conservation of angular momentum, which means they are inversely proportional because, so what I'm trying to say here, the quantity of motion given by RV remains to be constant, and V can be isolated and written as V is equal to constant divided by R, which means they are inversely proportional. The variation of these two quantities are not the same. So if one of them increases, the other is decreased, they are opposite. More importantly, when R decreases, then V increases, and that's because the gravitational force becomes stronger. Which means, let me say that this is the point A and that's the point B. As the moon is moving from A to B, R decreases, and we expect that the moon will be moving faster whenever it becomes closer to the Earth. This can be seen from the conservation quantity RV is equal to constant. Moreover, you can understand it because the gravitational pull becomes stronger. Okay, so using this relation, we can study the variation of R and V together. A moon moves faster when closer to a planet, while it moves slower at farther distances. This applies for both circular and elliptical orbits. By circular orbits, I mean if we're talking about two different orbits of two different radii, and elliptical orbit, I'm talking about the same elliptical orbit. Okay, so here both circular, I mean if you have two circular orbits of different radii, and this can be seen again from the relation given by V is equal to G central mass divided by R. Now moving to section 2, mechanical energy of a planetary system. So far everything that we have discussed is related to forces. Now we can interpret the same result using energy. Consider a planet of mass m and a moon of mass small m orbiting it at a distance r, where r is the center to center separation. The aim of this section is to express the mechanical energy of the system planet moon. Take the PE level to be very far away at r tends to infinity. The mechanical energy of the system in this case is given by, so the kinetic energy of the planet and the moon, so this should be small m actually, plus UG. UG represents the gravitational potential energy between the moon and the planet. Why here we have two kinetic energy but only one term for the gravitational potential energy? Because this term compensates for the coupling of both masses. Okay, unlike the kinetic energy, it can be present only due to one mass alone. However, the gravitational potential energy only exists if we have a coupling of two masses. Now, assuming that the planet is not moving or at rest, then we have the kinetic energy of the planet is equal to 0, and you can also understand this from the concept of inertia. We're assuming that the planet is much more inertial than the moon. Then the energy would be reduced into half mv square minus gmm over r. If the orbit is perfectly circular, then we can use the following relation, which is given by v is equal to the square root of gm over r, and eventually can be replaced here. Then the speed of the moon can be written in terms of this. Replacing it in the expression of the mechanical energy, we would get, now the power of 2 would cancel the square root, and we have the following. So rearranging these fractions, writing them in the same form as the following. And now we have half multiplied by a box. The box is given by g m over r minus the box. This would give us minus half a box. Then the mechanical energy of planetary system for circular orbit is given by the following. So remember that this cannot be used in an exercise. It should be derived from scratch, and this only works if the speed, or we're talking about circular orbits. So no need to memorize this, just remember the derivation. And the important thing is that in such type of cases, we take the PE level to be r tends to infinity. What does the PE level represent? It is the level in which the UG vanishes, and it is convenient to take it at infinity because there will be no more gravitational pull between the two masses. If the orbit is elliptical, then in this case we are only limited to this expression, which is given by the following. We cannot use any more that the speed is given by the square root of gm over r. Now section 3, a very important section, which is the escape speed. Consider a satellite of mass m orbiting a planet of mass m. The aim of this section is to determine the escape speed of the satellite. Then what do we mean by the escape speed? We know that the satellite is bounded by the planet by means of the gravitational force. Then if the satellite is given enough speed, that will make it lose the bound and become free very far away from the planet. Remember that in order for the moon to orbit the central mass at this location, we need to give it a certain speed dictated by the square root of gm divided by r. Here we're still talking about circular orbits. In the next class, we will talk how the variation in the speed would affect the shape of the orbit. The escape speed VE can be determined using the conservation of energy. So let me say here, if this satellite has been given the speed, which is radical gm over r, it will exist in this orbit dictated by the value of r. If it is given enough speed, more than this speed, which is known as the escape speed, then the satellite will lose bound with the central mass. Here we're assuming that the satellite will be at rest after the escape. Since there are no frictional forces, then the mechanical energy is conserved. So let me repeat and say, what is the escape speed? It is the speed that will be given to the satellite such that it will make it free from the bound to the Earth, and when it is free, its final speed would be 0. We can give it more than the escape speed, but here we're talking about the minimum amount of speed, which is the escape speed needed to be injected to the satellite in order to make it free from the bound. So the final state of the satellite will be at rest, and the final kinetic energy of the satellite is 0. Then we can apply the conservation of mechanical energy simply because we don't have any frictional forces, and the only force that is acting on the satellite to the moon is the pull of gravity, and this is dictated by the gravitational potential energy. Energy initial is equal to energy final, which means kinetic energy of the planet plus the kinetic energy of the satellite plus the gravitational potential energy between them is equal to the same terms in the final state. Now, assuming that the planet is at rest, then the kinetic energy of the planet in both initial and final state, they are 0. Now, the initial kinetic energy of the satellite would be given by half mve square. What does VE represent? It is the escape speed that has been injected initially to the satellite in order to make it escape. And because it will escape, then the final kinetic energy of the satellite would be 0, as given here. And the final gravitational potential energy would be 0 because at an infinitely large distance at the PE level, the satellite will lose the bound with the mass. In other type of exercises, we will see that we can give it an escape speed, or a speed which is larger than the escape speed, and in this case the final kinetic energy of the satellite won't be 0 anymore. Here we should place a term, and this depends on the exercise itself. And now we're solving for the escape speed. Then the escape speed is given by the radical 2gm over r. Then any massive body m to escape an orbit, let me scratch this, of central mass m should be given an initial velocity given by the square root of 2gm divided by r. So let me repeat and say again. Suppose we have a satellite here that is orbiting a central mass m at a distance r. In order to make this satellite escape the bound, we need to give it an escape speed given by the square root of 2gm over r. The direction of the velocity given to m is not important. So you might ask yourself, because velocity is direction and magnitude. Now we know the magnitude is given by that. How should be the direction of the velocity or the direction of the speed injected in order to lose the bound? It's not important. You can give it in any direction. Now we're gonna solve the following problem. A spacecraft of mass 1000 kilograms is an elliptical orbit about the Earth as shown above. So this is the Earth. This is the radius of the Earth. This is the orbit. And the moment they mention its elliptical orbit, we cannot use the relations given by the square root of gm divided by r, or the period is given by 4 pi r cubed divided by gm. These two relations, now they break down. We can only use the conservation of angular momentum given by r1 v1 is equal to r2 v2. And remember that even if we want to use this, we need to derive it from scratch. Now the mass of the spacecraft is given by 1 kk. At a point A, the spacecraft is at the distance RA given by 1.2 times 10 to the power 7 meters from the center of the Earth and its velocity of magnitude. So we have RA and we have VA. is perpendicular to the line connecting to the center of the Earth to the spacecraft. The mass and the radius of the Earth are given by the following. So the central mass is important and the radius of the Earth is important. Remember that RA is the distance from the center to the point A. Determine each of the following for the spacecraft when it is at point A. So before we start, let me take the PE level for the problem to be infinitely far away. So I have denoted here all the given that we might use, and let's start with part A. We need to determine the mechanical energy of the spacecraft, assuming that the gravitational potential energy is zero at an infinite distance from the Earth, as we have assumed. Then we know that the mechanical energy is given the kinetic energy of the spacecraft plus the gravitational potential energy. We're ignoring the kinetic energy of the Earth because we're assuming it is not moving, and that would be half mva square minus gme over re. We have all of the following quantities. We replace them. We will find that the mechanical energy is given by the following negative number. Now for part B, they're asking for the magnitude of the angular momentum for the spacecraft about the center of the Earth. Remember that if you want to calculate these two quantities, no need to mention any law because basically we're just calculating the quantities. The angular momentum is given by I omega. We know that I for a spacecraft about this axis of rotation is given by mr square, and omega is given by v divided by r. Replacing them, applying the cancellation effect, we have the mass, we have RA, we have A, and we will get the following number. And remember to be careful for the units. If you forget the unit of the angular momentum, this can be derived easily. Now the unit of I is given by kilogram meter square, and the unit of omega is given by radians per second, and this can be written as kilogram meter square per second because radian basically is not a unit. Now in part C, we are asked to determine the speed Vb of the spacecraft at the point B. The first mistake that you might do in this exercise is to use that V is equal to the square root of gm divided by r, since we have the central mass of the Earth and we have Rb, but this is not true, this is not circular, so we need to use the conservation of momentum. And here, because we're applying a law, we need to mention apply conservation of angular momentum, which means the angular momentum at point B would be equal to the angular momentum at point A, which is IB omega B is equal to IA omega A. Replacing them, applying the cancellation effects, then we would have RB VB is equal to RA VA, and we're searching for VB, which is given by the following fraction. Replacing the values, we would get that the speed is given by 2.37 times 10 to the power 3 meters per second. And here, let's do some interpretation. As you can see that we have the values of VA and we have the value of VB. Comparing them, we notice that VA is greater than VB, similarly because at the point A, the spacecraft is closer to the Earth. Now again, in part D, we need, so determine each of the following. In part D, the spacecraft, we need to determine the speed of the spacecraft if it is in a circular orbit around the Earth. And in part E, the minimum speed of the spacecraft at point A if it is to escape completely from the Earth. Now, in order to determine the speed of the spacecraft if it is a circular orbit, we need to use the relation which is given by V is the square root of gm divided by r, but this cannot be used directly. We need to derive it from Newton's second law. For this reason, I've mentioned here apply Newton's second law. Now, the net forces that are acting on the spacecraft are given by the pull of gravity, and let's do projection along the centripetal direction. That would be Fg equals to mac. Now, Fg is gmm over r, and here they should have mentioned, or I didn't write it, that we need to determine the speed of the spacecraft in its circular orbit around Earth at A. For this reason, I have substituted R for RA and V for VA, and now we can get that the speed is given by the square root of G central mass over RA. Replacing the values, we would get that the speed is given by the following. Here we're assuming that the orbit is perfectly circular. In part E, they're asking us to determine the minimum speed of the spacecraft at point A if it is to escape completely from the Earth. We know that the escape speed is given by the square root of 2gm divided by r, but we need to determine this using the conservation of energy. So energy at point A is equal to energy at infinity. Why energy at infinity? Because the final state would be the escape state. And that would be kinetic energy of the planet plus the spacecraft plus the gravitational potential energy computed or equated by two states, at the point A and the final states. And now we can directly neglect that for the planet, which is Earth. At infinity, that would be 0. Why this is 0? Because we're talking about the minimum speed to escape, assuming that at the escape the spacecraft would be at rest. And also u at infinity would be 0 because we have lost the bound between the spacecraft and the Earth. And we're left with the following: half mve square for this one and this for that. And now we're searching for ve square. We know that without surprises it would be given by the following expression. Replacing it would be 8.17 times 10 to the power 3 meters per second. What does this mean? Initially the spacecraft was orbiting the Earth at the point A with a certain speed. In order for the spacecraft to escape the Earth and to make it free, we need to inject the following amount of speed independent of the direction. And now for the rest of the video, we're gonna solve some exercises on what we have explained so far. A comet moves in an elliptical orbit around the Sun. Which of the following is at a maximum when the comet is at its farthest distance from the Sun? We know that when the distance is very large, the speed is minimum. No, not the kinetic energy, not the speed, not the acceleration, not the gravitational. So, is at its maximum? Yes, the gravitational potential energy is the correct answer. Why? Because it's given by UG equals to minus GMM divided by R. Although in value, this happens to be in value, this will decrease, but because it have a minus sign, then it will increase. Now exercise 2, a rocket has landed on planet X, which has half the radius of the Earth, then the radius changes by a factor of half. An astronaut on board the rocket weighs twice as much on planet X as on Earth. Then the weight on this planet, which is the gravitational pull, changes by a factor of 2. If the escape velocity for the rocket taking off from Earth is v0, then its escape velocity on planet X, we need to find the escape velocity on the new planet, but we know that the escape velocity is given by the square root of 2gm divided by r. Now already we know how does r changes. It changes by a factor of half. It's left to determine how does the mass of the new planet changes in terms of the planet of the Earth, and this can be determined from Fg is given by gmm divided by r square. We're interested in determining how does m changes. Then m is given by Fg r square divided by gm, where m is the mass of the rocket that doesn't change. Now we can apply the factor of change for this. The pull of gravity changes by a factor of 2, r changes by a factor of half, and g and m, they are invariant, so that would be 1 over 2, which means the central mass representing the mass of the planet X, it changes by a factor of half. And now if we apply the factor of change, that would be 1 multiplied by 1 multiplied by half multiplied by half. So that would be again 1, which means the correct answer would be C. A satellite of mass m is in a circular orbit with a speed v0 at a distance r from the center of Earth. What is the ratio of its escape speed from the orbit to its orbital speed ve? Now ve is given by the square root of 2gm divided by r, and the speed v0 is given by the square root of gm divided by r. Remember that these cannot be used in a free response unless we derive them from scratch. This is derived from Newton's second law. Also, this can be derived using the conservation of energy, and this is determined using the conservation of energy. So as you can notice that ve over v0 would be just a factor of radical 2, making A to be the correct answer. Now a comet moves in the sun's gravitational field following the path shown above. What happens to its angular momentum as it moves from point X to point Y? Now remember that in this case r decreases, the speed increases, but the quantity given by the angular momentum remains the same due to the net torque, which is equal to 0, so it remains constant. Now the elliptical orbit of a comet is shown above. Positions 1 and 2 are respectively the farthest and nearest position to the sun, and at position 1 the distance from the center to the from the comet to the sun is given by 10 times that at position 2, which means if this is r1 and this is r2, so r1 would be 10 r2. At position 2 the comet's kinetic energy is given by what? So at point 2 the speed would be greater, which means the kinetic energy would be greater, and we can directly say it is at its maximum value for the orbit because it's closest to the sun. Now exercise 6. The elliptical orbit of a comet is shown above. Positions 1 and 2 are respectively the farthest and the nearest position to the sun, and at position 1 the distance from the comet to the sun is 10 times that at position 2, which means r1 is equal to 10 r2. Now what is the ratio v1 over v2 of the speed of the comet at position 1 to the speed at position 2? This can be determined using the conservation of angular momentum, and we have that r1 v1 is equal to r2 v2, and remember that we cannot use this in a free response unless we derive it from scratch. We're interested in the ratio v1 over v2, which is basically r2 over r1 from this, and we know that rearranging this one we would have 1 over 10 is equal to r2 divided by r1, and that would be equal to 1 over 10, making the correct answer to be B. Now exercise 7. A moon of mass m orbits a planet of mass 49 m in an elliptical orbit as shown above. When the moon is at point A, its distance from the center to the planet is ra and its speed is v0. When the moon is at point B, its speed is 5v0. When the moon is at point B, the distance from the moon to the center of the planet is most nearly. This again, because we're talking about elliptical orbits, we can use the conservation of momentum, which is basically r1 v1 is equal to r2 v2. Now let me say this is A and that's B. At point A, the radius is given by ra and its speed is given by 5v0. That would be rb multiplied by v2. Sorry, this should be v0. rb multiplied by 5v0, and we're interested in ra over rb. Sorry, we're interested in rb in terms of ra. So v0 over 5v0 would be multiplied by ra is equal to rb, because we're interested in determining rb in terms of ra. So rb in this case would be 1 over 5 ra, making B to be the correct answer. And now finally, exercise 8 as an exit ticket. A rocket is launched from the surface of Earth with a speed v0 that will allow the rocket to escape the gravitational field of Earth. So this is the escape velocity. The same rocket is now launched from a different planet with the same mass as Earth. The mass is the same, but the radius changes by a factor of 4. Which of the following is the correct expression for the escape speed? We know that the escape speed is given by the square root of 2gm divided by r. This cannot be used in free response unless we derive it from scratch. Now we can apply the factor of change. 1 multiplied by 1 multiplied by 1 divided by 4, which means it's half, making the correct answer to be B. And that's it for me in this video, guys. See you soon in a new one.